Today in this module, we are going to learn about one of the important aspects of econometrics. So you will find that after this module, you would be able to understand the concept of classical normal linear regression model, the normality assumptions of disturbance term, the probability distribution of disturbance term, the probability distribution of OLS estimates, the properties of OLS estimates under normality assumptions, and ultimately about the normal chi-square, T and F distributions. So let us now try to understand about the classical normal linear regression model. The classical theory of statistical inference consists of two branches, namely estimation and hypothesis testing. Using the method of OLS, we were able to estimate the parameters of the two variable regression model. It was also shown that these estimators possessed several desirable statistical properties such as unbiasedness, minimum variance, etc., which means the property of blue, which is defined as best linear unbiased estimator. However, these estimators, they change from sample to sample, and we are not sure if they can represent the population parameters. Hypothesis testing deals with the issue of drawing inferences about the population regression function from the sample regression functions. To relate the estimated parameters B0, B1, sigma hat square to their true values beta 0, beta 1, sigma square, we need to know the probability distributions of B0, B1 and sigma hat square. So let us look at the probability distribution of the disturbance term mu t, on which generally these distributions depend. We know that B2 is equal to sigma Ci yi, where Ci was defined and is defined as xi upon sigma xi square. Now, since xi's are assumed to be non-stochastic and therefore fixed, B2 is a linear function of yi. Now, if you rewrite the above equation in terms of population regression function, we will obtain B2 equal to sigma Ci into beta 0 plus beta 1 xi plus mu I. Since Ci, beta 0, beta 1 and xi are fixed, B2 is a linear function of the disturbance term mu I, which is assumed to be random. So the probability distribution of B1 and similarly of B0 will depend on the probability distribution of mu I. Now, this assumption of probability distribution of mu I is therefore necessary for hypothesis testing. If we assume that mu I follows normal distribution and add this to the assumptions of the classical linear regression model, that is CLRM, we get the classical normal linear regression model, which is in abbreviated form known as CNLRM. Let us look at the normality assumption for mu I. The classical normal linear regression model assumes that each mu I is distributed normally, where normality could be defined, and this is distributed with expected value of mu I minus expected value of mu I into mu j minus expected value of mu j equal to expected value of mu I j equal to 0. Which means we are assuming that covariance of mu I, mu j is 0. And mean or expected value of mu I is equal to 0. Variance we are defining as expected value of mu I minus expected value of mu I square is equal to expected value of mu I square is equal to mu I square. And variance is defined as we did it earlier, that covariance mu I, mu j is equal to expected value of mu I minus expected value of mu I into mu j minus expected value of mu j, which is equal to expected value of mu I j equal to 0, where I is not equal to j because we are assuming that I and j are not equal. If they are equal, we get variance, and if they are not equal, we get covariance. Now, in a more compact form, the assumptions above can be stated as that mu I is distributed normally with mean 0 and variance sigma square. So this symbol which we have used here basically means distributed as, and n stands for the normal distribution. The two terms inside the bracket represents the mean and variance respectively. Now, since for the two normally distributed variables, zero covariance means that the two variables are independent of each other. So mu I and mu j are uncorrelated and independently distributed. Therefore, we can rewrite the above equation as mu I is distributed NID, in bracket we can write down 0 and sigma square. So this NID stands for normally and independently distributed. So let me repeat, we are saying that mu I is distributed with normally and independently with 0 mean and variance sigma square. The question which arises is, and which I am sure many of you may be having in your mind, that why do we need this normality assumption? Why is it necessary? So let me try to explain that to you, that why this assumption is required and why do we make this assumption. This disturbance term mu I represents large number of explanatory variables that are not introduced in the model, but they may have influence on the dependent variable. Now, we wish that the influence of this neglected variables or variable is small and at best random. The central limit theorem states that if there are a large number of independent and identically distributed random variables, the distribution of their sum will tend towards a normal distribution, as the number of such variables tends towards infinity, which means as it increases, this sum, as we have said earlier, would tend to be a normal distribution. The CLT therefore provides a theoretical justification for the assumption of normality of mu I, because we have said each mu I is independently distributed. A less restrictive version of the CLT states that even if the number of variables are not very large or strictly independent, their sum may still be normally distributed. The third reason for this normality assumption is that the probability distribution of OLS estimators can be easily derived with the normality assumption of the disturbance term mu I, because we know any linear function of normally distributed variables is itself normally distributed. So since OLS estimators B0 and B1 are linear functions of mu I and mu I is normally distributed, therefore one can prove that the two OLS estimators B0 and B1 are also distributed normally. Another reason is that the normal distribution involves only two parameters, mean and variance. So it is comparatively a simple distribution, and it is also well known that its properties are well studied and it has wider acceptability, therefore we use normal distribution. We also know that for a small sample size of less than 100 observations, the assumption of normal distribution is important, as it helps us to derive the exact probability distributions of OLS estimators, but also enables us to use the T, F and chi-square statistical tests for regression models. You also would appreciate that we are saying normality could also be useful because in large sample size, T and F test can still be applied even if we don't assume that the disturbance term is normally distributed. So having understood the reason for this assumption of normality, let us now try to understand the properties of OLS estimators under normality assumptions. The OLS estimators, they basically possess certain properties under the normality assumptions. They are unbiased. They have minimum variance among the class of linear estimators, which combined with the unbiasedness property means that they are efficient among these unbiased estimators. They are also consistent estimators and converge to their population values or true population values. The fourth property under normality is that the OLS estimators B0 being a linear function of mu I is normally distributed with mean expected value of B0 equal to beta 0 and variance of B0 equal to say sigma B0 square is equal to sigma xi square upon n into sigma xi minus x bar square into sigma square, or variance of B0 is equal to sigma square B0 is equal to sigma xi square upon n sigma xi minus x bar square into sigma square. Or in a more compact form, it can be written as B0 is distributed normally with the beta 0 and sigma B0 square. Now this implies that the variable z, which is a standard normal variate, can be defined as z is equal to B0 minus beta 0 upon sigma B0, and it follows the standard normal distribution with zero mean and unit variance. Or in other words, z is distributed with mean 0 and 1 and is a standard normal distribution. The OLS estimator B1 being a linear function of mu I can also be similarly defined as a normally distributed with mean expected value of B1 equal to beta 1 and variance of B1 equal to sigma B1 square into sigma square upon sigma x minus x bar square. I'm sure you are familiar with these results which we have discussed in our earlier modules also. Now, in a more compact form, this can be written as B1 distributed normally with mean beta 1 and variance sigma B1 square. Then the variable z, which is defined as z is equal to B1 minus beta 1 upon sigma B1, also follows the standard normal distribution. Now these can be represented in terms of graphs, and you will find that in figure 1 we have the distribution of beta 1 and the distribution of or beta 0. And similarly we can also have the distribution of a standard normal variate z for B0 and z for B1. Now you may also find that we can also define n minus 2 into sigma hat square upon sigma square is distributed as the chi-square distribution with n minus 2 degrees of freedom. That is, n minus 2 into sigma hat square upon sigma square is equal to n minus 2 into s square upon sigma square, and this is distributed as chi-square with n minus 2 degrees of freedom. So sigma hat square is nothing but the estimated value and sigma square is the true value. Now this knowledge of distributions will help us to draw inferences about the true sigma square from the estimated sigma hat square, which is also denoted as s square. The next property is that the OLS estimators B0, B1 are distributed independently of sigma hat square. Another property which is also important is that the OLS estimators B0, B1 under the assumption of normality have minimum variance in the entire class of unbiased estimators, whether linear or not. This result due to Rao is more powerful than Gauss-Markov theorem, which is restricted only to the class of linear estimators. So Rao theorem basically relates to both linear as well as non-linear estimators, and Gauss-Markov theorem relates to mainly the linear estimators. Thus, OLS estimators are not only blue, but are best unbiased estimators blue as well in terms of the linear and non-linear. So we may define them as the minimum variance in the entire class of unbiased estimators, and hence can be written as MVUE minimum variance unbiased estimators. Let us conclude, therefore, the assumption of normal distribution of disturbance term mu I enables us to derive the sampling distributions of B0 and B1, both normal and sigma hat square related to the chi-square. Now this allows us to construct confidence intervals and conduct hypothesis tests. When we assume that mu I is distributed normally with mean 0 and variance sigma square, and yi being a linear function of mu I, we have in that case mu I is itself normally distributed with mean and variance given by. So when we assume that mu I is distributed normally with mean 0 and variance sigma square, and we know yi being a linear function of mu I, then we find that mu I is itself normally distributed with mean and variance given by expected value of yi equal to beta 0 plus beta 1 xi, and variance of yi comes out to be equal to sigma square, which is same as variance of mu I. So in other words, we may say that yi is distributed normally with mean beta 0 plus beta 1 xi and variance sigma square. Now, having understood the distributions of yi and earlier of b0 and b1, let us now look at the student's T statistic. Now, we have b1 distributed normally with beta 1 and sigma b1 square, and b0 distributed normally with beta 0 and sigma b0 square. Now, we convert the normally distributed OLS estimators into z variable, which we already know are also distributed as normally with mean 0 and variance 1. We convert the normally distributed OLS estimators into z variable, which are distributed as normally with the 0 mean and variance 1. Now, so we can define zb0 equal to b0 minus beta 0 upon sigma b0, which comes out to be equal to b0 minus beta 0 upon sigma xi square upon n sigma xi minus x bar square into sigma square whole under the root. And this is equal to zb0 is equal to b0 minus beta 0 into under root of n sigma xi minus x bar square divided by sigma xi square, and whole divided by sigma. This is distributed normally with mean 0 and variance 1. Similarly, we can define zb1 equal to b1 minus beta 1 upon sigma b1, and is equal to b1 minus beta 1 upon under the root sigma square upon sigma xi minus x bar square, which we had defined as variance, and we have the under root now. Now, this gives us zb1 equal to b1 minus beta 1 into under the root sigma xi minus x bar square whole divided by sigma, and this we know is distributed normally with mean 0 and variance equal to 1. Now, if we substitute s square for sigma square, where sigma square is generally not known, then we will have tb0 equal to b0 minus beta 0 upon sb0, and we may in that formula which we had discussed earlier substitute sigma square by s square. But now when we define zb0 equal to b0 minus beta 0 into under the root n into sigma xi minus x bar square upon sigma xi square upon s, it is distributed as t with degrees of freedom n minus 2. Similarly, we can also write down tb1 equal to b1 minus beta 1 into under root sigma xi minus x bar square upon s, which is also distributed as t with n minus 2 degrees of freedom. The degree of freedom here is n minus 2 because we are dealing with simple linear regression model and we are estimating two parameters beta 0 and beta 1. Now we get the distribution because the numerator is a standard normal variable and denominator is a chi-square distribution. I'm sure you would recall that S square is equal to sigma EI square upon n minus 2, which is a sum of n minus 2 independent chi-square variables, and so S square itself is distributed as chi-squared with n minus 2 degrees of freedom. Now let us look at few more important probability distributions. We look at very few important probability distributions which will be used extensively for statistical inference of OLS estimates. Now the first important, which we have already discussed in detail, and again I am trying to briefly remind you about it, is the normal distribution. So normal distribution, as you all know perhaps, is the most popular probability distribution with bell-shaped figure. A normally distributed random variable x has the following probability density function, which is that fx is equal to 1 upon root 2 pi sigma into exponential x minus mu square upon 2 sigma square, and the value of x lies between minus infinity and infinity, or infinite and minus infinite to plus infinite. Now in this distribution you will find that u and sigma square are parameters of the distribution and they represent mean and variance respectively. The normal distribution is shown in the figure, and you can see is a bell-shaped distribution. But in this bell-shaped distribution, the peak or the central point is at the mean, which we have denoted by mu, and as you increase the variance or as you go to the right and to the left, you will find that the interval basically increases from 68% to 95% to 99.7%, which is given by mu plus minus 1 sigma, mu plus minus 2 sigma, and mu plus minus 3 sigma. Now let us repeat and understand what are the properties of the normal distribution. Some of the important properties are that the distribution is symmetrical around its mean value. The area under the normal curve that lies between the values of mu plus minus sigma, as the figure also shows, is approximately 68%. Between mu plus minus 2 sigma is approximately 95%, and between mu plus minus 3 sigma is 99.7%. Another property which is very important is we can obtain a standardized normal variable z from a given normally distributed variable x with mean mu and variance sigma square as follows, which is that z is equal to x minus mu upon sigma square. I'm sure you know we have used it earlier in our module today itself. This standardized normal variable z has zero mean and unit variance. The probability distribution function of the standardized normal variate therefore is very simple and is as follows. Fz therefore is equal to 1 upon root 2 pi into exponential of z square by 2. Now we usually denote a normally distributed variable as x distributed as n with mean mu and variance sigma square. Now this symbol, as we said earlier, is the symbol of distributed as. And similarly, we can write down the distribution for a standardized normal variable z, which would be, in this case, z is distributed normally with mean 0 and variance 1, or which is also known as unit variance. Another important property in a normal distribution is a linear combination of normally distributed variables is itself normally distributed. In terms of formulas and variables, let's try to understand it. So let's say that x1 is distributed normally with mean mu 1 and variance sigma 1 square, and similarly x2 is distributed normally with mean mu and variance sigma 2 square, and suppose both of them are independent variables. Then the linear combination of both the variables can be written as follows, which is y is equal to ax1 plus bx2, where a and b are constants. We can then show that the distribution of y is normal and its mean is equal to a mu1 plus b mu2, and the variance is equal to a square sigma 1 square plus b square into sigma 2 square. Let me remind you, this is under the assumptions of independent variables, which means x1 and y1 we have presumed, or x1 and x2 in this case we have presumed are independently distributed. Let us look at another property which is of central limit theorem. We have briefly discussed or mentioned about it earlier. So suppose x1, x2, xn represent random variables which are independent of each other, and all of them have the same distribution in terms of probability, and let's presume expected value of xi is equal to mu and variance of xi is equal to sigma square. Then the sample mean tends to be normal distribution with the mean mu and variance sigma square as the number of observations increases to infinity. In terms of symbol, it can be written as x bar is distributed with mean mu and variance sigma square by n, as n tends to be infinite or infinity. Now consider a random variable. What is a random variable? That you know. So let us consider z is equal to x bar minus mu upon sigma by root n, which is same as root n into x bar minus mu upon sigma. The random variable will tend towards standard normal. So z is distributed normally with mean 0 and variance equal to 1. Now let us look at the test of normality. A normal distribution will always have skewness equal to 0 and kurtosis equal to 3. In other words, a normal distribution is symmetric and mesokurtic. So to find out if a distribution departs from normal distribution, we need to check if the computed values of skewness and kurtosis are different from 0 and 3 respectively. The formal test can be done by Jack-Barra test of normality, which is defined as follows: JB equal to n into s square by 6 plus k minus 3 square by 24, where s means skewness and k means kurtosis. Now under the null hypothesis, JB is distributed as a chi-square statistics with 2 degrees of freedom. Students, you can see in this formula that if skewness is 0 and kurtosis is 3, then both the terms, the first term and the second term in the bracket, will tend to be equal to 0, and therefore the Jack-Barra statistics will be close to 0. The mean and variance of a random variable which follows normal distribution are independent of each other. This is another property which is very useful in econometric literature. Let us take an example. So this is our example number 1. Suppose that x follows a normal distribution with mean of 6 and variance of 9. That is, x is normally distributed with mean 6 and variance 9. Find the probability that x will take a value between x1 equal to 3 and x2 equal to 9. What is the solution? Let us look at the solution. So we first calculate the value that z takes, which is as follows: z1 is equal to x1 minus mu upon sigma, and therefore is equal to 3 minus 6 upon 3 in our current example, and is equal to minus 1. Similarly, z2 is equal to x2 minus mu upon sigma and is equal to 9 minus 6 upon 3 is equal to 3. Now we use table under normal distribution to find the probability that the two values of z will take. So probability of z between 0 and 1 is equal to 0.3413. By using the notion of symmetry, we have probability of Z greater than -2 or less than equal to 0 is equal to 0.3413. Therefore, the probability that X will lie between X13 and X29 is 0.3413 plus 0.3413, 0.6826. Let us now look at the second distribution, which is the chi-square distribution. Now, if Z1, Z2, Zk represent an independent standardized normal variable, that is Z is equal to, or Z is distributed normally with mean 0 and variance 1, then the quantity V equal to Z1 square plus Z2 square, Z3 square up to Zk square is said to possess the chi-square distribution denoted as chi-square k with k degrees of freedom. Here, degree of freedom means the number of independent variables that are summed up to make the quantity V. The chi-square distribution is shown in our figure 3, where you have the density on the y-axis, which is fx square or f chi square, and on the x-axis we have chi square. And what we observe is that as the value of k increases, the distribution becomes more symmetrical. So let us now look at the properties of chi-square distribution. The chi-square distribution has a skewed distribution, and the degree of skewness depends on the degree of freedom. When the degree of freedom are less, the distribution is highly skewed to the right, and the distribution becomes more symmetrical as the degrees of freedom increases. And when the degree of freedom exceeds 100, the variable which is under root 2 chi square minus under root 2 k minus 1 becomes a standardized normal variable where k is the degree of freedom. The second property is that the chi-square distribution has a mean k and variance 2k, where k is again the degree of freedom. The third and the final property is that for two independent chi-squared variables Z1 and Z2 with k1 and k2 degrees of freedom, their sum, that is Z1 plus Z2, is also a chi-square variable with degrees of freedom equal to k1 plus k2, which means the sum of their degrees of freedom. Let us take an example. Example 2. Find the probability of getting a chi-square value of 32 or greater, given that the degree of freedom is 14. Let's look at the solution now. Using the table from chi-square distribution, we find that the probability of getting a chi-square value of 31.3193 or greater for a degree of freedom of 14 is 0.005. So, the probability of getting a chi-square value of 32 or greater is less than 0.005, which is a small probability indeed. Let's now move on to another distribution, which is known as student's T distribution. Now suppose Z1 is a standardized normal variate, that is Z1 is distributed normally with mean 0 and variance 1, and Z2 is another variable which follows chi-square distribution with k degrees of freedom. And if both Z1 and Z2 are independent of each other, then the variable t could be defined as Z1 upon under root Z2 by k. Now this is equal to Z1 under root k upon under root Z2. Now this follows student's T distribution with k degrees of freedom. It is usually denoted by Tk, and T with a subscript k, where k denotes the degrees of freedom. And this T distribution is shown in figure 4, where you may have again student's T distribution for various degrees of freedom, and we have for k equal to 5, k equal to 20, and k equal to 120, which is almost a normal distribution. So let's see what are the properties of T distribution. The T distribution is also a symmetrical distribution and therefore is similar to the normal distribution. However, it is flatter than normal distribution, but as the degree of freedom increases, normal distribution approximate T distribution, or I should say T distribution approximates a normal distribution. The T distribution also has a mean of 0 and variance of k upon k minus 2. Let's look at example on this, which is our example 3. So when the degrees of freedom is 21, what is the probability of getting a t value of let's say about 2 or greater, b about minus 2 or smaller, and c of modulus t of about 2 or greater value. Modulus t denotes the absolute value. The solution is that the probability of getting a t value of about 2 or greater when degrees of freedom is 21 is about 0.025, which you can see from the table of T distribution. Now, since T distribution is symmetric, the probability of getting a T value of about minus 2 or smaller when the degrees of freedom is 21 is about 0.025. So the probability of getting modulus T value of about 2 when the degree of freedom is 21 is about 0.05, and which we may say is the double of 0.025, which is 0.025 into 2. Let's now look at another important distribution, which is the F distribution. Now in F distribution, suppose we have two independently distributed chi-squared variables, namely Z1 and Z2, whose degrees of freedom are k1 and k2 respectively. Then we can define the variable f equal to z upon k1 whole divided by z2 upon k2, and it follows Fisher's F distribution with k1 and k2 degrees of freedom. Now it is usually denoted by f k1 k2, where k1 denotes degrees of freedom of numerator and k2 denotes degrees of freedom of the denominator. The figure for F distribution is shown in figure 5, and you can again see that we have different graphs for different degrees of freedom, and as the degrees of freedom of both k1 and k2 increases, the distribution again tries to be normal. So what are the properties of F distribution? Let's see them one by one. The first property is that the F distribution is similar to chi-square distribution and is skewed to the right. The F distribution approaches normal distribution as k1 and k2 gets larger. We also can say that the F distribution has a mean of k2 upon k2 minus 2 for k2 greater than 2, and variance is equal to 2k2 square into k1 plus k2 minus 2 upon k1 into k2 minus 2 whole square into k2 minus 4, and this is for k2 greater than 4. An F distribution with 1 and k degrees of freedom is equivalent to the square of T distribution with k degrees of freedom. In other words, T square with degrees of freedom k is equal to F1k. Now, there also exists a relationship between F and chi-square distributions. If the denominator degrees of freedom of F distribution k2 is large enough. That is, k1 into F is distributed as chi-square k1. Note that all the three distributions, T, F and chi-square distributions, are related to normal distribution. They all tend to approach the normal distribution when the degrees of freedom get larger and larger. Example 4. Find the probability of getting a F value of about 1.6 or greater when k1 is equal to 10 and k2 is equal to 8. Answer: from the F table we can see that the probability is equal to 0.25. Give a numerical example to show that K1F is approximately equal to chi-square K1 when K2 is large. The answer is, suppose K1 is equal to 20 and K2 is equal to 200. The critical value of F is 10%, or at 10% is 1.46. So K1F is equal to 20 into 1.46 equal to 29.2. From the chi-square table, the current chi-square value at 10% for degrees of freedom equal to 20 is given by chi-square 20. In the bracket we can write down alpha, which is 10%, equal to 28.412. Now, having understood this, we move on to another important distribution in statistics and econometrics. It is Bernoulli distribution. A random variable x follows Bernoulli distribution if its probability density function is as follows, which is that probability x equal to 0 is equal to 1 minus p, and probability x equal to 1 is equal to p, where p is equal to between 0 and 1 and is also known as the probability of success of a particular event. Now, for such a variable, expected value of x is equal to 1 into probability x is equal to 1 plus 0 into probability x equal to 0. This comes out to be equal to p. Similarly, variance of x is equal to p into q, where q is equal to 1 minus p and is defined as the probability of failure. So q is the 1 minus p. Another distribution is the binomial distribution. Now, let n represent the number of independent trials, each of which results in a success with probability p and a failure with probability q, which is equal to 1 minus p. The number of successes in n, number of trials, is represented by x. Then x follows binomial distribution, whose probability density function is fx is equal to ncx into p raised to power x into 1 minus p raised to power n minus x, where x is the number of successes in n trials, and where n by x or ncx is equal to n factorial upon x factorial into n minus x factorial. So n factorial is read as n factorial and is equal to n into n minus 1 into n minus 2, so on till 1. The binomial distribution has two parameters, namely n and p. So in binomial distribution, we have expected value of x equal to np and variance of x is equal to npq, or np into 1 minus p. Let's take an example of this binomial distribution. A new treatment for swine flu has 20% probability of complete cure. On trial basis, 35 patients were given a treatment. What is the probability at least 10 patients will be cured completely? The solution is that let x is the number of success in 35 trials. We need to find probability of x greater than 10. From the binomial distribution table, we find that probability of x greater than 10 is equal to 0.1457. So we can say that the probability at least 10 patients will be cured is equal to 0.1457. Let's look at another distribution, the Poisson distribution, which is a discrete distribution. A random variable x follows a Poisson distribution if its probability distribution function is given as fx is equal to e raised to power minus lambda, lambda raised to power x upon x factorial, for x equal to 0, 1, 2 up to a particular number, which could be n, which is finite, and lambda is greater than 0. Now there is only one parameter lambda in this Poisson distribution. Now, one important characteristics of this Poisson distribution is that the expected value of lambda is equal to its variance, which means we are saying that expected value of x is equal to variance of x is equal to lambda. The Poisson model is useful in modeling infrequent or rare phenomena such as number of accidents during festival seasons, or number of telephone calls during next 10 minutes, or the number of birth delivery in a maternity ward during Sunday. After discussing all these distributions, let us now try to take stock and summarize our entire discussion. We have studied the classical normal linear regression model in this chapter. Also, the classical normal linear regression model is understood and is different from the classical linear regression model. Under the CNLRM model, the disturbance term mu I entering the regression model is assumed to be normally distributed. We have also learned that the CNLRM does not require any assumption about the probability distribution of mu I. It only requires that the mean value of mu I is 0 and its variance is a finite constant. We have also learned that the central limit theorem provides the theoretical justification for normality assumption. According to CLT, if x1 to xn be a random sample and expected value of xi is equal to mu and variance of xi is equal to sigma square, then the distribution of random variables Zn is equal to under root n into x minus mu upon sigma, and it converges to standard normal, which is with mean 0 and variance 1 as n increases to infinity. We have also learned how when we assume that disturbance term is normally distributed, the OLS estimators are best unbiased estimators, which means we can say they are BUE instead of BLUE. The OLS estimators under the normality assumption follow well-known probability distributions. The OLS estimators of the intercept and the slope are themselves normally distributed, and the OLS estimator of the variance of mu t is related to the chi-square distribution. The normal distribution we have seen is the most popular probability distribution and has a bell-shaped picture. The other important distributions we have learned include chi-square distribution, student's t distribution, F distribution, the Bernoulli distribution, the binomial distribution, and in the end, the Poisson distribution. Thank you, students. Thank you very much.